Hey, let's talk about birthday bound implications. So in the lecture, we've seen this very simple generic attack against a collision-resistant hash function. And that is, we just choose q of n many random bit strings of length 2n. Then we hash all of those, and then we check whether we have found a collision among those hashes. And as it turns out, the success probability of this adversary is not that bad. So the probability of finding a collision if I choose q of n random values is at least this. Now the most important message is that there's a q of n squared in this thing. And because of that, if I do 2 to the L operations for some L, and because in my success probability the q of n is squared, I get from 2 to the L operations, I get 2 to the 2 times L loss in security, meaning success probability will be something like 2 to the 2 times L over something instead of 2 to the L. So for that reason, because I get this 2 in the exponent for free, essentially the length of these hashes needs to be twice as long as usual to compensate for the 2 that I get for free here. And in this analysis, we do kind of this worst case assumption about the hash function, meaning that the hash function is as good as possible against this attack. And this worst case assumption is that the hash values are actually uniformly distributed. So if I choose a uniform pre-image, I get a uniform image. So that's something you get if the 2 to the n possible images of this hash function all have the same number of pre-images of length 2 times n. So for example, we don't know this for SHA-2 or something because they are too chaotic to analyze in this sense. If the hash function is such that there are images that have many pre-images, then this attack actually only gets better. Why? Because if I have this whole bunch of pre-images that hash to the same hash value, then it's kind of likely that if I choose random pre-images, that I will get one here and that I will get another one here, because it's less likely to get one here or here in the other buckets for other hash values. So then if I choose them uniformly at random, it's kind of likely I get some in this larger bucket that all hash to the same value. And then it gets more likely that I will actually get a hash collision because those two already hash to the same hash value. If all of these buckets are equally large, then also my distribution will hit each bucket with the same probability, and then this minimizes the probability that I ever get this two values into the same bucket. But if one bucket is more likely than the other buckets, it's also more likely that I get two random values in this particular bucket. However, showing this is not too straightforward, so we have this special case in lemma 910 that's kind of easier to understand, that only looks at what happens if I only choose two random values. So in theory, this doesn't break anything, right? Because this probability here, the q of n times q of n minus 1 over 2 to the n plus 2, that's still negligible. So q of n is just some polynomial if I have a polynomial time adversary, and we divide by something that's super polynomial. So this doesn't really change anything in theory. That's still negligible. However, in practice, this has very important implications, because in practice we can't just say, oh, it's negligible. We also need to choose an n that we're comfortable with in practice, so that the success probability here becomes small enough for the security parameter that we're choosing. And so in particular, all of the hash values that we're choosing, the hash lengths, they need to be large enough so that this success probability of this generic attacker is actually small in practice also. So let's look at some concrete numbers. It's kind of difficult to guess like how many hashes is something that like computers can compute and what our adversary is capable of in terms of runtime. But as a rough estimation of what kind of computations are possible, let's take the hash rate of the Bitcoin network. So if you remember, for Bitcoin, there are like huge number of people that burn a lot of electricity to compute hashes very quickly. And because this is a significant fraction of the energy that humanity is producing, it kind of makes sense to see this as like an indicator of how much computation is possible. So the Bitcoin network uses like 0.2% of the world's energy supply, meaning that we're off like at most a factor of 500 of what like the world would be capable of computing using the current power supply. So the Bitcoin network today has a hash rate of approximately 100 exahashes per second. So this would be 10 to the 20 hashes. That's roughly 2 to the 66. So we can take this as an indicator of kind of how much computation is possible on this world. And then I took this nice table from Wikipedia, which lists a bunch of example values for birthday attacks. So this tells you if your hash function has this many possible outputs and you want this success probability, then you need this or this many operations to find a collision with that probability. So for example, if there was a hash function with like 128-bit output, which is like 128 bits would be a normal size for like an AES key or something. In that context, it would be considered secure because it's like impossible, completely impossible to brute force 128 bits. However, for hash functions, because of this birthday bound, the situation is a little bit different. And if I take a look at how many operations I need to do in order to get a probability of 3/4 to find a collision, then that's just like 10 to the 19. So this is something that the Bitcoin network will just like break in a second. Of course, as a disclaimer, obviously the Bitcoin miners, they don't actually have like that much storage necessarily to do 100 exahashes and store these values to later compare them. But this is just as an indicator of like, okay, this is certainly in the range of humanly possible. Because at least computing that many hashes is easily possible. You can do it within a second, apparently. So that's why there's no hash function that has 128 bits output, even though 2 to the 128 is like a huge number. So if we then take a look at SHA-2, for example, which has several levels of security, a 256-bit output is the like lowest level of SHA-2, as far as I know. And there we're looking at way larger numbers. So if I want to have a chance of like at least 0.1%, then I would have to do 10 to the 37 operations. So how much time would that take for the Bitcoin network? If we divide the number of hashes that we need by the hash rate, then we get that this will take approximately 10 to the 17 seconds. How much is that? There we're talking about 3 billion years, so this is fine. So that's why 256 bits is at least the standard for hash functions. Usually like the 348 and the 512-bit output is also pretty common. Because you always have to keep in mind that this is like the most stupid attack, so there's nothing about this hash function. So you probably want some margin to account for more sophisticated attacks. But yeah, any hash function with just 128-bit output, not a good idea. Lastly, let's talk about other consequences of this birthday bound that we have. Because this idea of trying to find collision through random choices, this is something that appears in other contexts as well. In particular, you may remember the randomized counter mode that we had in the lecture. So this is an encryption mode, and whenever I encrypt a new message that may consist of multiple blocks, I choose a new random counter, and then I throw counter plus I into a PRF and XOR the result with a message to get my ciphertext block. And in the analysis, we've shown that this is CPA secure. And this proof went as you would think. You replace this PRF with a random function. And then if this is a random function, then essentially from the ciphertext, you get no information about the messages because they are just uniformly random, except if you repeat one of these counters. Because then you get the same PRF value twice, and then you learn the XOR of these two messages. And that is exactly the scenario that we had in one of our lemmas. That's basically just if you do Q random choices, like we would doing these counter choices, then the probability that two of them collide is at least like this Q squared something. So essentially the same table that we just had applies here too. Of course, here things are less bad. So if you take this counter of length 128 bits, then you're kind of fine, because after 10 to the 18 encryptions, you may see a collision with probability 1%. And 10 to the 18 encryptions is actually something that, well, it's also like in the realm of possibility, so I wouldn't rule this out, but it becomes less likely. So in the CPA security proof that we did back then, we weren't too concerned about this birthday bound stuff, because there we essentially only cared about this one challenge ciphertext. So one fixed counter or range of counters that were interesting to us, and we just compared it to all of the Oracle queries. All right, this was a little bit of a walk into more practical stuff. Thank you for listening, and see you.